This is next unit, Unit 10. We're talking about liquids, solids, and solutions. So the first thing we talk about today, we're talking about the states of, or the states. We'll be able to state the characteristics of solids, liquid, and gases, and then identify the 5 types of intermolecular forces. So first of all, we started out, we understood this, that liquids and solids are considered to be condensed states of matter. Unlike ideal gases, which have no attractive forces, they actually attract to each other. This attraction was that actually brings them together and form a bond, literally pulls them out of the gaseous state. Goes from a gas back to a liquid. A liquid, as their bonds get closer and closer together, they turn into a solid. Knowing the actual specific states about characteristics about the states of matter, you should know this actual chart. Great chart to know. Understand the gases, liquids, and solids. Understand that gases have no definite volume, know that they have a definite shape. Liquids have a definite volume but no definite shape, and the solids have both a definite volume and definite shape. Just know the characteristics here about this stuff. It's very, very helpful going forward. Great multiple choice questions can come from this. Next, we'll talk about the intermolecular forces. So far this whole way through, we've talked about, let me get through this really quick. We've talked down here about intramolecular forces. Back with nomenclature, we were forming chemical bonds. With chemical bonds, we were talking about their structures and what type of shape they are. Is it an AX2, AX3? Is it linear, trigonal, planar? We were talking about that, but it's all based upon the intramolecular forces, what's within the compound. But now our focus is going to be on the inter. Inter means between. What's the bond that holds one water molecule to another water molecule, or it's what we call the intermolecular forces. And the strength of an intermolecular force is going to affect, again, the actual boiling point and melting point. So when actually something boils or melts, the bonds must break. What bonds specifically? They are the intermolecular forces. So let's take a look at 5 of them. We're going to start with the strongest. We're going to work our way to the weakest. The first one is the ionic. Or first of all, again, making that point, you see at the very beginning, intermolecular forces, generally weaker than the intra, and they actually would hold them together. So types, here we go. The first type are the ion-ion. Now first of all, understand this. All these intermolecular forces are based upon a positive-negative attraction, just like we see here with the ion-ion. The ion-ion, though, is going to be our strongest because a positive and negative is a definite positive and a definite negative. Why? Because the electron's been transferred. Remember that? There's a difference in electronegativity above 2.0, therefore the electron was finally transferred. Example here would be sodium chloride. Sodium is a +1, chloride is a -1. Now what's unique about this, all you have to realize to look at an ion-ion, all you're looking for is an ionic compound. All it is an ionic compound like sodium chloride. So by default, you're looking at anything that falls, any metal that falls in group 1 or group 2, bound with a non-metal in group 17. If you see that, by default, you can say ionic compound. Once you see ionic compound, you know for sure the intermolecular force is an ion-ion. What's unique about this one is the exact same force that holds one sodium to one chloride, one cation to one anion, is the same force that holds billions of sodium chlorides together. Ion-ion, that's our strongest. Then we get to an ion dipole. Now what happens is our charges actually become a definite, like we'll see with the actual sodium, and then we have a partial on the oxygen side. If you remember oxygen, or actually remember water, H2O, was a polar molecule. If you remember, again, it was bent, bond angle 104.5. And we realized as we drew polar arrows going towards the oxygen, the arrows did not cancel each other out. In fact, they actually joined forces. So the movement went above the oxygen, you became negative. That was the most area where you gained electrons. And between the hydrogens, it was positive. So what we realize here is we actually have an ion sodium or an ion magnesium joins up with a dipole. In the example of water, we call it a ion dipole. Now which one of these is stronger? I just look at the charge. So magnesium is a 2+. It's going to have a stronger charge. Just kind of think about it this way. The stronger the charge of a magnet, the stronger the bond it's going to have. So magnesium has a stronger charge and a stronger bond. Ion-ion are strongest. Ion dipole. Now I move to dipole-dipole. Dipole-dipole is unique because now I have partial charges. And so we see a HCl here. we see that as a partial negative and a partial positive. The arrow points towards the chlorine because the chlorine has a higher electronegativity. It's pulling the electrons more, it's winning the battle, becoming partially negative, and the hydrogen is losing, becoming partially positive. Their difference is still less than 2.0, so we don't call it ionic yet. It is a polar molecule. Or in other words, it has two poles, it is a dipole. So if I then see by this compound alone it's a dipole, I then know if one HCl binds to another HCl, it becomes a dipole-dipole bond. There's our example of dipole-dipole. So we can actually just keep on joining together. I can tell by just looking at the compound alone. Now the next two we're going to deal with are hydrogen bond and dispersion. Both of these are once again a type of dipole. The hydrogen is a strong type of dipole, whereas dispersion is a weak one. So first let's take a look at hydrogen. Hydrogen is unique because with hydrogen it is a dipole. So you see a water molecule, it is a dipole. But when I look at a compound, I recognize a dipole, but I take a closer look and I see that within the compound, hydrogen comes in contact with FON. We're talking fluorine, oxygen, or nitrogen. Not all three, but just one of them. And I see with water that hydrogen comes in contact with oxygen within, and I'm safe to assume if they come in contact in the intra, they will be present in the inter, like we see here. And so between my water molecules, I have what we call then a hydrogen bond. So again, if hydrogen comes in contact with fluorine, oxygen, or nitrogen within, you're safe to assume it's present between. The next type of dipole is dispersion. And dipole in this dispersion, is very, very weak. Commonly what happens are these are atoms or molecules that are just normally neutral, but then what happens, they get distorted. And how they get distorted is, remember, what's moving around the nucleus are electrons. So if you have a Hd positive come by, what happens, it actually distorts the actual structure because all the electrons chase after Hd positive, making one side negative, the other side positive. So something is normally neutral now has two poles, it now is a dipole. So then they were actually linked together. It doesn't matter whether it's an actual anion or a cation, or it's the positive charge of another dipole that comes by. Negative electrons chase after it, therefore distorting the structure, creating a dipole. You usually go back to its shape, therefore it's weak. The next one is hydrogen bond example here. Now H2, we see H2, again, they're sharing the electrons equally, they're equally balanced here. They are neutral. All of our diatomics are nonpolar, therefore they're held together by dispersion only. But what happens, again, once again, Hd positive comes by. Hd positive just distorts the whole situation because all those electrons are going to chase after Hd positive, causing one side to become negative, therefore the other side positive, and it distorts its structure. You see it's now distorted. It's not balanced. So one side's gaining, the other one's losing. I've just created a dipole. I have a partially negative gaining, a partially positive losing. This is the dipole, bound to a dipole, bound to a dipole, bound to a dipole. So all the hydrogens happens to them all at the same time. Therefore, they link together and they form a dipole-dipole bond. Once again, it is weak. So really, the strength of the dispersion force depends on the number of electrons, which brings us to the term polarizability. Polarizability is just the ease of electrons to shift. And so we realize the larger the atom, the greater the number of electrons, the easier the shifting takes place, the more electrons you have present. So example we see here between helium and xenon, xenon being the larger, yes, has more electrons, therefore it's going to shift easier. So basically is this, if we're looking at nonpolar, held together by dispersion only, and I want to compare one dispersion to another dispersion and see what's stronger, all I realize I have to do is look at its molar mass. All I have to do is look at its molar mass. The larger molar mass wins. The larger molar mass wins. It's that simple. So let's talk about, I've been mentioning this a couple of times, nonpolar held together by dispersion only. Let's talk about three examples of nonpolar. The first example of nonpolar is when we have a carbon and a hydrogen only in a compound. We call it a hydrocarbons. All hydrocarbons are nonpolar. It doesn't matter if it's CH4, it could be C2H6. It doesn't matter how many carbons or hydrogens you have, but when you have carbons and hydrogens together, they're called a hydrocarbon. All hydrocarbons are nonpolar. therefore held together by dispersion only. A second example are hop wrinkles, H2O2, F2, Br2, iodine, I2, N2, Cl2. All those hop wrinkles are nonpolar. They are held together by dispersion only. The last example of nonpolar, we're going back to our chemical bonding unit, are ideal geometries. AX2, AX3, AX4, tetrahedron, AX5, trigonal bipyramid, AX6, octahedron. As long as the x's are the same, ideal geometries are nonpolar, therefore held together by dispersion only. So sum it up. Dispersion is the weakest, ion-ion is the strongest. And then you kind of know the list between. So ion-ion is the strongest, ion-dipole, then hydrogen, then dipole-dipole, then dispersion is our weakest. Remember, when something boils or something melts, intermolecular forces must break. So the melting point and boiling point of a substance is dependent upon the strength of its intermolecular